So for each logical connective that we introduced, there have been a few components to what you had to learn about it. There was syntax, semantics, and then there's rules. And for the new symbols that I'm going to introduce, there will also be these components or analogous components. And I thought it would be good to just take a step back and remind ourselves what is meant by these terms. So syntax refers to kind of the grammar. And here, as an example, I'm going to use conjunction, the and symbol, so this wedge. So syntax is kind of grammar, meaning it's a component that just tells us, what parts of speech fit in different places, like nouns, verbs. Here it's propositions. So you take a proposition, you stick a wedge between them, and overall you get a proposition. That's grammar, that's syntax. And it just tells you things like, this is good, A equals B and C equals D. That's good because it's proposition, that's proposition, and it's overall a proposition as a consequence. But this is bad. This is an error here because you can't put C on the right. C is a term, and you're supposed to put a proposition. So that's pure grammar. It doesn't tell you what anything means. What gets at meaning is semantics. So this statement here is semantics, is when we say the symbol phi wedge psi is supposed to mean that phi and psi are both true. That's what it's supposed to mean. This is semantics. How do you interpret the symbols and generate meaning, generate ideas or facts about the world from the symbols? Usually in mathematics, you're not going to generate facts about the actual world, but you'll generate facts about the mathematical world. Semantics are not so much used for proving things. They're used for developing your imagination and interpreting what things are meant to mean and becoming inspired to come up with different ideas of proof, or becoming inspired with guesses for what might be true or what might not be. But it's not so much involved in proofs. Rules are what drive formal proofs. So rules are things like this. From phi and psi, you may deduce phi. From phi and psi, you may deduce psi. From phi and psi, you may deduce phi and psi. So these rules are things you sort of have to be told, or they have to be declared at some point as accepted rules for the and symbol. If the and symbol is to work in the way that we think it ought to work given the semantics for it. So what I'm going to do now is introduce syntax, semantics, and something like rules for a whole bunch of new mathematical symbols. So I have mainly been using the term rules to refer to the rules of logical deduction. And that's not a universal thing, that's just the terminology that I've been using here. Now that we're transitioning into developing the mathematical, into developing set theory, what's going to take the place of rules is going to be axioms and definitions. So for each new thing, we're going to introduce some syntax, some semantics, and so like the grammar of it, how to interpret what it's trying to say, which is not so helpful for proofs, but it's helpful for understanding what is the intention. And finally, axioms and definitions, which are what actually helps drive your arguments in proofs. And in today's lecture, for the new symbols that I'm introducing, I only want to go through syntax and semantics. So I'm going to leave the axioms and definitions till next time. That means you will be left unable to prove anything. So proof is going to be impossible, but you will be able to determine whether things are grammatical or not, and you'll be able to interpret what things are supposed to mean, or intended to mean, even though you don't necessarily know how to use that to form arguments yet.